Okay, let's unpack this. There's a really fundamental challenge right now in getting complex reasoning capabilities to work effectively on smaller, more accessible models. We're diving deep today into a pretty novel solution for this problem. It's something that really plagues the current generation of open source language models. I mean, their inability to reliably learn these intricate multi-step reasoning processes, especially when you train them on really challenging expert data. So we're discussing Supervised Reinforcement Learning, or SRL. It's a framework designed pretty specifically, it seems, to get around the major limitations of the standard training methods, the ones we usually rely on: Supervised Fine-Tuning, SFT, and Outcome-Based Reinforcement Learning, RLVR. And the tension here is it's critical, and the source paper lays it out very clearly. When you take these smaller, maybe more resource-constrained models, let's say something in the 7 billion parameter range, and you throw these really hard reasoning problems out of the stuff they call DOER, well, the success rate just plummets. It starts near zero. And in that scenario, SFT, the fine-tuning, it tends to overfit, right?
Right.
It actually degrades performance sometimes.
It does. It struggles badly.
While RLVR, the reinforcement learning part, it basically starves. There's no useful reward signal coming through.
Precisely.
Yeah,
Gradient information.
So the SRL framework comes in with this, quite ingenious solution, I think. It reformulates the whole problem-solving thing. Instead of one big output, it's a sequence of logical actions, discrete steps.
Mm-hmm.
And crucially, it applies dense, stepwise supervision to each one of those actions. So our mission today, for those of you really immersed in ML architectures and data science, is to do a proper professional detailed analysis. We're going to break down the technical methodology, really scrutinize these dense objective functions they're using, and dive deep into the empirical results. And they test it across two very different but equally challenging domains: competitive math reasoning and practical agentic software engineering.
What's fascinating here, and the paper really emphasizes this, is just how severe this failure mode is on dollars. It's not a minor issue. When you're dealing with problems where the policy model, the language model you're training, just cannot find the right answer, its success rate is negligible. Well, outcome-based RL is structurally handicapped in that situation.
Because the reward is just binary, correct or incorrect.
Exactly, purely binary. Correct, final answer, you get a positive reward. Incorrect, you get 0 or negative. And if the model can't even stumble upon a single correct solution within its rollout budget, let's say dollar attempts,
which is likely on these hard problems.
Very likely. Then the training signal is just uniformly negative or 0. It's flat. The policy basically gets no information on how to improve. It doesn't know which way to adjust its parameters.
Right, no direction.
Now contrast that with SFT. SFT is, of course, essential for initializing models, teaching them basic structure and instruction following. But the sources confirm, and this is key, when you apply it to these long, intricate expert demonstrations, especially the ones derived from these difficult dollared problems, SFT forces this really rigid token-by-token imitation.
Like it has to match the expert exactly.
Pretty much. And with a modest amount of data, which is often the case, and particularly with a less capable student model, like a 7B parameter model trying to learn from a much larger expert, well, SFT training doesn't really promote robust, generalizable reasoning. Instead, you often get these shallow reasoning behaviors. And crucially, as you mentioned, you see measurable performance degradation compared to the base model it started from.
Which is kind of counterintuitive, isn't it? You'd expect fine-tuning to always help.
You would, but the rigidity kills the generalization needed for complex reasoning. It highlights why we need a new approach, one that keeps the supervision, because we need guidance, but grants more flexibility than just token matching.
And that's the promise of SRL, then?
That's the central promise, yes. SRL aims to provide a dense and, importantly, smooth learning signal exactly where these traditional methods fail. It uses sequence similarity rewards calculated at each step.
So not just at the end.
Not just at the end. At every logical action the model takes, it generates a continuous score, like how similar is this generated step to the expert step. This means you get gradient information, useful updates, even when the entire solution path, the full rollout, is ultimately incorrect. It allows for much richer policy updates, continuous learning, even in these really hostile reward landscapes where standard RLVR just completely stalls due to that sparsity problem.
Okay, that makes sense. It's bridging that gap, providing signal where there was none. So to really appreciate why a new framework like SRL might be necessary, and frankly why it involves this added complexity, we absolutely need to spend some time digging into the specifics of why the existing methods fail. Let's look at the forensic evidence, so to speak. starting with Supervised Fine-Tuning, SFT. What are its precise failure modes on complex reasoning? Fundamentally, SFT works by minimizing a negative log likelihood loss. The objective is LLS theta YXIA. Basically, it tries to maximize the probability of the model predicting the very next token correctly, given the preceding tokens in the input prompt.
Standard language modeling objective, essentially.
Exactly. And for many tasks, this works really well. It maximizes the conditional probability of the generated sequence matching the expert sequence perfectly. But like you said, in the context of complex multi-step reasoning problems, the drawbacks really start to bite.
They really do.
The source material is quite explicit here. This objective leads to extreme rigidity. When the demonstrations are long and the logical steps within them are nuanced, which they always are in, say, advanced mathematics or complex coding, the model gets penalized heavily for any deviation from the expert's exact token sequence.
Even if the deviation is logically sound, perhaps just a different way of expressing the same step.
Right. It learns to parrot the specific path, the exact sequence of tokens the expert used, rather than internalizing the underlying, more flexible logical structure of the solution. And this inevitably forces overfitting, especially, as you pointed out, when the student model, say our 7B parameter example, has limited capacity compared to the sheer complexity of the expert data, like reasoning traces from a much larger model like DeepSeek R1.
And we see the hard numbers in the paper that absolutely confirm this. The empirical evidence from their math reasoning setup is, frankly, startling. They took the Quen 2.57b instruct-based model and fine-tuned it directly on the challenging S1K dataset using SFT. The resulting model, called S1K7b, well, it didn't just fail to improve, it actually saw performance decline significantly.
How much?
Take the AMC23 benchmark, a standard competitive math test. The base Quen model achieved an AVG at 32 score of 49.3. Pretty respectable. After SFT training on S1K, the S1K7B model's score plummeted. It dropped drastically to 24.1.
Wow, that's nearly half.
It's a massive drop. This isn't just a failure to learn effectively, it's catastrophic performance degradation. It clearly shows the limitation of trying to capture high-level logical complexity through rigid token-level imitation.
So the fine-tuning process itself, aimed at improving reasoning, actually destroyed the existing reasoning capabilities.
In this specific context, yes. That degradation perfectly illustrates the limits of standard supervised distillation where applied to these very hard reasoning problems. SFT seems fundamentally ill-suited when the goal isn't just mimicking a sequence, but distilling a high-level, generalized reasoning capability.
Okay, so SFT creates rigidity, leads to overfitting, and can even destroy performance. The natural next thought is, okay, let's use reinforcement learning. Reward the model for getting the right answer, ignore the specific path, that's RLVR, often using algorithms like GRPO. But here, the problem flips completely, doesn't it? It becomes about reward sparsity.
Exactly. RLVR is purely outcome-based. It relies on that simple binary signal. 1 if the final answer is correct, 0 or maybe -1 if it's incorrect. The critical issue arises on these Dow-hard problems, which are defined precisely by their high difficulty relative to the policy model's inherent capacity. Let's think about a complex algebra problem needing, say, 8 distinct logical steps to solve. If our 7B parameter policy model isn't capable enough to consistently get all 8 steps right, or even just gets 1 step wrong early on,
then the final answer is wrong.
The final answer is wrong. The reward is uniformly negative or 0. And because the model is highly unlikely to just randomly discover a fully correct 8-step solution within a typical limited rollout budget taller, the reward landscape it perceives becomes overwhelmingly flat and uninformative, mostly just negative signals.
It's lost in a desert of wrong answers with no signposts.
That's a good analogy. And this is where the mathematical mechanism kicks in the problem of the vanishing advantage estimate. The GRPO objective, which is commonly used, relies on this group-level normalized advantage estimate. It's calculated as AIT is AIE text. Now think about what happens if all the rollouts in a batch are uniformly incorrect.
All the rewards still are the same negative value.
Correct. Consequently, the mean reward is equal to each individual reward tilde dogs. But most critically, the standard deviation of the rewards, text tilde, which measures the spread,
It goes to 0 because there's no spread. All rewards are identical.
Exactly. The standard deviation approaches 0. And when that term in the denominator of the advantage estimate goes to 0,
Division by 0. The advantage estimate, AIT, either vanishes or becomes mathematically undefined.
precisely. Either way, you can't calculate a meaningful policy gradient. Geometrically, you can picture the policy landscape. The model is sitting on this vast, flat plane of incorrectness. Since there's no local variance in the reward signal, everything looks equally bad. The gradient calculation tells the model nothing about which direction might lead to improvement. It doesn't know which way is up.
So the training just stalls, completely stalls.
It stalls because the environment, through this sparse reward, provides zero directional information. Even if the model was, say, just one minor calculation error away from a fully correct solution on one of its rollouts, RLVR doesn't capture that proximity.
It's an incredible failure of information flow, isn't it? You have this potentially powerful neural network ready to learn, but the signal about what constitutes goodness is so incredibly sparse that the entire learning mechanism, the gradient calculation, just collapses.
It collapses. Now, there are mitigation strategies, of course, things like dynamic sampling, which was used effectively in methods like DAPO. The idea there is to basically keep drawing samples and filtering batches until you get one that contains a guaranteed mix of both successful and unsuccessful rollouts.
So you force some variance into the batch?
You force the condition $0 to be true. This ensures the standard deviation is non-zero, allowing the advantage calculation to proceed.
But that sounds computationally expensive.
Yeah.
Especially on hard problems where successes are rare.
It can be very expensive. And more fundamentally, even when you find such a batch, it still doesn't resolve the core issue. It doesn't provide any signal about the quality of the incorrect rollouts. What if the model took 3 excellent, logically sound steps but then failed on the 4th? RLVR still gives it a 0 or negative reward, same as a rollout that was nonsense from step 1. There's no partial credit.
Right, no granularity.
And that's precisely the gap SRL is designed to fill. It aims to provide that dense, continuous signal at every single decision point, rewarding partial progress and logical soundness, not just the final outcome.
Okay, so now we transition to the proposed solution. This is where SRL comes in with its quite elegant fix, really.
Right.
It tries to address both the rigidity of SFT and the sparsity of RLVR simultaneously. And it does this by fundamentally changing the unit of decision-making. The core idea, as we touched on, is to transform this complex problem-solving process. Instead of generating one monolithic sequence of tokens, it reframes it as a sequential decision-making process. And each logical step in that process becomes a discrete action.
That decomposition is the first key step.
Let's dig into this action-based formulation. They take an expert trajectory, the full correct solution yeller, and then methodically break it down. It becomes a sequence of steps, and each isn't just arbitrary tokens. It's defined as a logical action. It's the minimal, concrete operation needed to actually advance the solution towards the final answer.
Like one step in an algebraic simplification.
Exactly. Or in the software engineering context they explore, maybe it's executing a specific shell command or writing to a file. The beauty here, they argue, is that this concept is pretty domain agnostic.
Yes, the framework itself doesn't intrinsically care if it's math or code.
By decomposing the problem this way, you take this huge, potentially overwhelming, high-dimensional problem space, generating a long proof or complex code patch, and you break it down into a series of smaller, hopefully more manageable, decision points, action by action.
And that decomposition directly enables the next crucial part, the stepwise training data construction. This is how they create the data for localized supervision. From a single expert solution that has, say, dollar logical steps, they actually generate Nellalana distinct training instances.
Okay, how does that work?
For any given step colors in the sequence, from 1 to n to 1, the input prompt provided to the model, let's call it step, consists of 2 things. The original problem description, 6 delellers, plus the entire history of the correct preceding expert logical steps show Dale Day Tall.
So it knows the context up to that point.
Exactly. It has the full correct partial solution so far. And the model's task, its target, is only to predict the single immediately following logical action, the expert's Dale tech.
I see. So it's not predicting the whole rest of the solution, just the very next move.
Just the next logical move. This approach inherently grants more flexibility than standard SFT because the policy model isn't being forced to imitate the expert's entire remaining token sequence from that point on. And they refine this further by introducing the concept of the inner monologue. This is quite interesting.
The Langle text thinkags.
Yes. The policy is explicitly prompted using a specific system prompt to first generate its own internal reasoning or planning. This gets encapsulated within these Langle tags. Let's call this the text part. Only after generating this internal thought process is the model supposed to commit to outputting the required logical action.
So there's a structure enforced, think first, then act.
Precisely. The system prompt, as described in the paper, rigorously enforces this. It tells the model something like, draft your thoughts within think tags until you are confident. Then, provide only the single next logical step required. This decoupling is critical. It means the model's internal thought process, its text, can actually diverge quite significantly from whatever implicit reasoning the expert might have used.
As long as the final action is correct.
As long as the resulting logical action is high quality and moves towards the solution. This promotes generalization, allowing the model to develop its own reasoning style, rather than just mimicking the expert's implicit thoughts.
That distinction between the internal thought process and the external verifiable action seems absolutely crucial. It sounds like you're trading the really tight rigidity of next token prediction in SFT for a different kind of structural constraint, this mandate for a specific output format. Think, then action. But how does SRL ensure the model doesn't just overfit to the expert-specific logical structure now, instead of the underlying flexible reasoning logic we wanted to learn?
That is an excellent question, and the answer lies squarely in the reward mechanism they designed. It's key to understanding how SRL balances guidance with flexibility, moving beyond simple imitation. The shift is enabled by the dense sequence similarity reward. Unlike SFT, which demands exact token matching for the entire sequence, or RLVR, which only cares about the final binary outcome, SRL provides a continuous reward signal. It's no white text step, calculated based on the quality and, importantly, the semantic alignment of the generated action desk compared to the expert's correct action for that specific step.
Okay, continuous reward. How is it calculated? What makes it dense?
Let's define QO clearly, based on the paper. The reward function is given as $1 is frac2 part. Here, $2 represents the total number of elements, like tokens or characters, depending on implementation. In the two sequences being compared, the generated action, $7, and the expert action, $7. So $2 equal S1 plus S2 is the crucial part. It's the total count of elements that are found within all the non-overlapping matching blocks between the two sequences.
Non-overlapping matching blocks.
Yes. This is where the algorithmic sophistication comes in. The comparison uses an algorithm that's conceptually very similar to, say, Python's difflib sequence matcher. It finds the longest contiguous block that matches exactly between $7 and $7.2. Then it recursively looks for the longest matching blocks in the parts of the sequences before and after that first block.
Okay, so it's finding all the chunks that match up, even if they're separated by different stuff.
Exactly. $0 is the sum of the lengths of all these matching chunks identified by the algorithm.
Tell us more about why this specific measure, finding these non-overlapping matching blocks, $, is fundamentally better at capturing, say, logical correctness or semantic similarity compared to something simpler, like just counting matching tokens, Hamming distance, or using a standard cross-entropy loss on the action step.
That's a great point. A simple token-level loss or Hamming distance is often too brittle. It's overly sensitive to minor variations, things like local reordering of terms, slight formatting changes, extra white space that often don't actually affect the logical meaning or the correctness of the step, especially in math or code. Think about mathematical expressions or code snippets or maybe long bash commands with several arguments. What we really care about is the integrity of the logical components within that action.
The core meaning.
Yes. The difflib style approach. By identifying these longest common subsequences and recursively finding all the non-overlapping matching blocks $, effectively captures whether the essential components of the action, the variables, the operators, the function names, the specific shell arguments, are present and sequenced correctly relative to each other. It's robust to minor variations in the surrounding syntax or ordering if the core elements match up.
Can you give me an example?
Sure. Let's say the expert action is a simple algebraic step. X equals 2y plus 5. If the model generates x equals 5 plus 2y, a pure token comparison might score this poorly because the sequence is different. But the sequence similarity reward, $5 based on matching blocks, would likely be very high, maybe even 1.0, because all the essential components, x, xl, 5 plus sub 2 place y, are present and the relationship is preserved. It focuses on content alignment, not just demanding exact token parity.
Okay, that's a significant shift in perspective. You're essentially grading the model on the semantic integrity of its proposed action, not just its ability to perfectly mimic the expert's keystrokes. And crucially, you mentioned this dense reward is calculated only on the logical action part. It completely ignores the inner monologue, the text thing part.
Exactly. That's a critical design choice outlined in the paper. The reward computation explicitly excludes the Langle text think wrangle block. This ensures the optimization process is laser-focused on improving the quality of the outputted logical steps, the things that actually interact with the problem state or the environment. It simultaneously preserves the model's freedom to develop its own internal style of planning and reasoning within the think block without being penalized for deviating from the expert's implicit thought process.
But what if the model just fails to follow the format? Like, it forgets the think tags or outputs something that isn't a parsable action?
They handle that with a strong penalty. If the output fails to adhere to the required structure, for instance, if it doesn't produce a valid action command after the think block, or maybe forgets the required function tags in the software engineering task, it receives a sharp negative reward explicitly mentioned as dull equals not sour. This acts as immediate strong feedback to maintain the necessary structural adherence for the whole system to work.
Got it. So this dense reward signal, which lives in the range $0, $11 for valid actions, plus the sharp $1 penalty for format errors, is then fed into the policy optimization process. They use the GRPO objective, right? But you mentioned earlier there was a technical adaptation needed for dynamic sampling. Can you clarify the difference between how dynamic sampling works in standard RLVR versus this SRL adaptation? The distinction seems important.
Yes, it's a critical implementation detail that highlights the difference density makes. In standard RLVR, as we discussed, dynamic sampling is used to combat reward sparsity. It filters batches until it finds one containing a mix of successful outcomes, reward of 1, and unsuccessful outcomes, reward of 0 or -1. The whole point is to ensure the standard deviation of the binary rewards in the batch is non-zero, so you can calculate a meaningful outcome-based advantage estimate. Now, for SRL, the reward dollars is already dense and continuous, living mostly between 0 and 1. So the problem isn't usually getting zero variance because all rewards are identical negatives. Instead, the potential issue is getting very low variance because all generated actions in a batch happen to be similarly good or similarly bad according to the sequence similarity measure.
Why is low variance still a problem if the rewards are continuous? Doesn't any variance allow for a gradient?
Technically, yes, but a near-zero variance provides a very poor, noisy learning signal. Think about it. If the variance of the sequence similarity scores across all the rollouts for a specific step is extremely low, say close to 0, it means all the different actions the policy tried for that step were almost equally good or equally bad when compared to the expert's action. For example, if all rollouts score an $2 value around 0.8, there's minimal difference between them. The advantage calculation, which relies on tilde, will produce values very close to 0 for all rollouts. This again hinders effective differential learning. We need sufficient variance to clearly inform the model which specific variations in its generated action led to the marginally better score, say $1.99, versus the marginally worse one, say $4.70.
Okay, so low variance, even with continuous rewards, implies the policy isn't really exploring effectively at that step, or maybe it's already converged locally.
Exactly. Low variance suggests that the policy might be stuck in a flat region of this stepwise reward function, or perhaps it's already quite good and the differences between rollouts are negligible. So the dynamic sampling adaptation for SRL filters out batches where the standard deviation of the sequence similarity reward scores across the rollouts falls below a small positive threshold, epsilon dollars. The condition for keeping a sample batch for training is effectively text similarity.
So it ensures you only train on steps where the policy's different attempts actually produced meaningfully different similarity scores. You focus the training effort where there's a clear signal-to-noise ratio for learning that stepwise differentiation.
Precisely. It ensures that the gradient updates are based on informative comparisons. And we should probably briefly mention the computational impact noted in the paper regarding batch sizes. It's quite revealing.
Wow.
They report using a batch size of only 128 for the standard GRPO RLVR baseline, whereas for SRL, they could use a much larger batch size of 512.
Why the difference?
It's likely a direct consequence of the filtering rate driven by reward density. Because GRPO's sparse binary reward led to very high rejection rates when trying to find mixed outcome batches for the difficult S1K math data, they probably needed a smaller batch size to maintain training stability and throughput. SRL's dense continuous reward signal, combined with its variance-based filtering, results in a much higher frequency of useful batches, satisfying epsilon. This lower filter rate allows them to leverage larger, more computationally efficient batch processing, 512 samples per batch, without running into the same stability issues.
Okay, the technical foundation for SRL seems really solid. It addresses the core issues conceptually. Now let's turn to the evidence. Do the empirical results actually confirm that SRL can overcome these deep-seated training challenges, especially on hard reasoning tasks? We'll start with the mathematical reasoning domain. Just to recap the experimental setup quickly. The base model was Quen 2.57b instruct. The training data came from S1K 1.1, that's 1,000 very challenging math problems, sourced from competitions paired with high-quality reasoning traces generated by the DeepSeek R1 model. And the crucial pre-processing step, as you mentioned, was parsing these potentially complex, free-form solutions into structured, numbered steps. Each step needed to represent a clean, ground-truth logical action for the SRL training process.
That data preparation is non-trivial but essential for SRL.
Right. And then for evaluation, they used several demanding benchmarks, AMC23, AME24, AME25, and the Minerva Math dataset. The key metrics reported were average at 32, FG at 32, which measures performance with multiple samples, and greedy accuracy, which is just single best guess.
Now, looking at Table 1 in the paper, the performance comparison is quite stark. It really paints a clear picture, and we need to focus on these numbers to truly grasp the impact of the different training paradigms. Let's just quickly reiterate the baseline failure modes we discussed. SFT, Supervised Fine-Tuning on the S1K data, wasn't just ineffective, it was actively harmful to reasoning performance. Remember the AME24 greedy accuracy. The base Quen model started at 13.3%. The SFT-trained model, S1K7B, just plummeted to 3.3%.
A devastating drop.
Absolutely. It shows that over 90% of the original model's capability on that specific metric was essentially wiped out by trying to rigidly imitate the complex expert paths. Now, RLVR, using GRPO with the binary outcome reward, managed to avoid this catastrophic collapse, which is good. It maintained generalization, but it showed only very marginal gains over the base model. For instance, on AMC23 AVG at 32, RLVR achieved 52.0, only slightly better than the base model's 49.3.
Which supports the reward sparsity argument, right? It couldn't learn much because the signal was too weak on these hard problems.
Precisely. The marginal improvement confirms that on $, the sparsity really prevents significant progress via outcome-based RL alone, at least with this setup.
Okay, so SFT failed badly, RLVR barely moved the needle. How did SRL perform when used on its own?
SRL standalone showed a substantial and, I think, meaningful improvement across the board. This is the first indication that the dense, stepwise supervision strategy is actually working as intended. On average, across all the benchmarks and metrics reported in that table, SRL provided around a 3.0% absolute increase over the strongest baseline, which was usually the base model itself or sometimes RLVR.
Can you give a specific example?
Let's stick with AME24 greedy accuracy for consistency. Base model was 13.3%, SFT was 3.3%, RLVR was likely similar to the base or slightly better maybe, though not explicitly broken out for every metric comparison baseline. SRL standalone boosted performance to 16.7%.
Okay, so from 13.3% to 16.7%, that's a solid jump.
It's a solid 3.4 percentage point jump on a really challenging competitive math benchmark. That signifies, I believe, a genuine improvement in the model's learned reasoning process, not just superficial changes in output quality. It's learned to take better logical steps. However, perhaps the most compelling finding presented in the paper is the synergistic result achieved by sequencing the training methods, the SRL right RL RLVR pipeline.
So train with SRL first, then fine-tune further with RLVR.
Exactly. The idea is to use SRL first to teach the model how to perform robust, stepwise decision-making, to build that foundational capability of generating sound logical actions. And then, once the model has that ability, apply the outcome-based RLVR to refine the overall coherence and correctness of the final answers. This sequential approach achieved the highest overall performance reported in the study, resulting in about a 3.7% average absolute increase over baselines.
That sequential strategy seems really key then. SRL acts almost like a powerful curriculum initializer. It teaches the fundamentals of stepwise reasoning first.
That's an excellent way to put it. SRL effectively bootstraps the reasoning process, making the problem tractable for the model. What were the peak results for this pipeline approach?
Looking at the table, the SRL right RO RLVR pipeline achieved an AMC23 AVG at 32 score of 52.1, and maybe more impressively, it pushed the AME24 greedy accuracy all the way up to 20.0%.
Wow, 20.0%. Let's put that in perspective. The base model was 13.3%. SFT collapsed it to 3.3%. RLVR alone maybe got it to around 14-15%. SRL alone got it to 16.7%. But the pipeline combining them hits 20.0%.
That difference is enormous, especially in the context of competitive math scores.
It really is. It strongly validates the hypothesis that SRL isn't just another alternative method, but potentially an essential curriculum component when you're trying to tackle these really difficult dialer reasoning tasks, particularly with smaller open source models. It solves that initial problem of signal sparsity and intractability, providing a high quality, structured starting point, which subsequent outcome focused refinement like RLVR can then build upon effectively.
Okay, the performance metrics are definitely convincing. SRL, especially when pipelined with RLVR, delivers significant gains. But the really deep dive has to go beyond just the scores and focus on why it's successful. We need to dissect the components of the SRL methodology itself and try to confirm that each part is actually contributing. Let's start by revisiting the dynamic sampling adaptation for SRL. Was it really necessary?
That's a fair question. The sources provide evidence that the adaptation of dynamic sampling, DS, specifically for SRL's continuous rewards, was indeed beneficial, not just a carryover from RLVR. Table 2 in the paper presents a direct ablation study. SRL trained with dynamic sampling versus SRL trained without it. The results are quite clear. Looking at the average greedy score across the math benchmarks, SRL trained without DS achieved 24.7%. However, when they activated the variance-based dynamic sampling, that score boosted significantly to 27.6%.
So roughly a 3% absolute gain just from adding that filtering step.
Yes, nearly 3 percentage points. That's a non-trivial performance improvement, and it directly confirms our earlier technical discussion. Simply having a continuous reward signal isn't quite enough on its own. The training signal derived from that reward must also be sufficiently varied across the different rollouts within a batch. If the model consistently generates actions for a step that are all, say, 70% similar to the expert's action, the variance will be low. Filtering out those low variance batches prevents the model from wasting computation on updates derived from samples that lack the clear differential information needed to calculate an informative advantage estimate. SRL's dynamic sampling ensures the training focuses on the frontiers of exploration, those steps where the policy is actively making different choices that result in measurably different reward outcomes.
Okay, so the dynamic sampling adaptation is validated.
Yeah.
This brings us directly to the core design choice of SRL, the granularity of the supervision itself. The study explicitly compared 3 different levels of guidance granularity, which is really helpful for isolating the unique benefit, if any, of SRL's stepwise decomposition approach.
Exactly. That comparison, shown in Table 3, is crucial for understanding why decomposition helps. They compared 3 distinct reward function setups. First, the standard final answer reward, RLVR, sparse, binary, outcome-based. Second, they tested what they called holistic sequence similarity, one step. Here, the model generates the entire solution trajectory in one go from start to finish. Then, the sequence similarity reward, using the same Dynabol equals 2MT logic, is calculated by comparing this whole generated sequence against the entire expert trajectory. So, still dense, but applied globally to the whole solution.
One similarity score for the whole thing.
Right. And third, the proposed multi-step SRL approach, where, as we've discussed, the task is decomposed and the dense local similarity reward is applied individually to each generated logical action, step by step.
Okay, what did that comparison show?
The results demonstrated a clear hierarchy. The holistic similarity approach did perform better than the sparse RLVR baseline. This makes sense because it provides some dense gradient signal. Even if the final answer is wrong, if the generated solution is partially similar to the experts, it gets some credit. We saw this, for instance, on the AME24 AVG at 32 metric. RLVR scored 11.1%, while the holistic one-step approach improved that slightly to 11.7%.
So some benefit from just using sequence similarity at all.
Yes. But the key finding was that the multi-step granular guidance of SRL provided a much clearer jump in performance. On that same AME24 AVG at 32 metric, SRL pushed the score up significantly further to 13.2%.
So going from 11.7% with holistic similarity to 13.2% with stepwise similarity, that's another 1.5 percentage points just from changing the granularity of the reward application.
Precisely. And while 1.5 percentage points might sound small in isolation, on these incredibly challenging competitive math benchmarks, that represents a very significant margin. It's often the difference between getting a few more problems right.
What does this tell us about the learning mechanism then? Why is granular better than holistic for these tasks?
It empirically validates the core hypothesis, the value of decomposition. For highly complex, multi-step problems, asking a model, especially a smaller one, to generate a single, very long sequence, hundreds of tokens, and then trying to reward its overall similarity to the expert path is still too coarse a signal. The model struggles to perform effective credit assignment. Which specific part of its long generation actually contributed positively or negatively to that final similarity score?
It's hard to know where it went right or wrong within that long block.
Exactly. By forcing the model to commit to smaller, individually verifiable actions sequentially. Step 1, output action 1, get reward 1. Step 2, output action 2, get reward 2. And so on, the reward signal becomes exquisitely precise and localized. The model gets immediate feedback on the quality of each logical step. This allows it to more easily identify and correct specific errors in its logical flow or calculations. The learning is focused, concentrated, allowing the smaller model architecture to handle the overall task complexity without getting overwhelmed.
This localization of the learning signal, focusing on the quality of individual steps, apparently translates into fundamentally different and seemingly more sophisticated reasoning behaviors observed in the models trained with SRL. The source material makes a point of highlighting that these models move beyond just outputting static monolithic solution blocks.
Yes, the qualitative analysis of the model outputs is highly revealing, according to the paper. Instead of the kind of rigid, often single-block reasoning structures you might see from SFT-trained models, the SRL-trained models encourage and exhibit more flexible, dynamic planning that actively integrates the inner monologue with the external logical action steps. They observe 3 distinct emergent behaviors worth noting.
What were they?
First, they saw instances of upfront planning. In these cases, the model doesn't just dive into calculations immediately. It sometimes begins its response with an explicit high-level plan outlined within an initial think block. This plan details the subsequent logical steps it intends to take, almost like setting a cognitive anchor or strategy for the rest of the generation. Example 2 in the paper apparently shows this.
Okay, so it thinks about the whole path first. But then, when it starts executing that path, does it stick rigidly to the initial plan?
Not necessarily, and that leads to the second emergent behavior, on-the-fly adjustments. The paper reports that SRL models frequently insert multiple distinct reasoning blocks, additional think sections throughout the solution generation process, not just at the beginning.
So it pauses mid-solution to think again.
Exactly.
Yeah.
It suggests an iterative reasoning process. The model might execute an action, observe the result implicitly or explicitly, and then pause to reevaluate the state, perhaps update its plan, or perform complex sub-step planning within a new think block before committing to the next logical action. It looks much more like dynamic iterative problem solving rather than just executing a predetermined script.
That sounds much more like how humans often tackle complex problems.
It does seem analogous, and the third behavior reinforces this. Reflective verification. They observed instances where the model pauses, often near the end, to reflect on an intermediate result or even the final derived answer before outputting the ultimate solution statement. Examples 1 and 3 in the paper are cited as illustrations.
Like double-checking its work.
It looks very much like that. It suggests the model might have learned a capability for self-correction or validation, using its inner monologue capacity to review its reasoning or calculations. This could significantly reduce the probability of simple arithmetic errors or logical flaws propagating through a long solution chain and ruining the final answer.
These emergent behaviors, planning, adjusting, verifying, sound impressive. But whenever we see performance gains, especially paired with increased use of things like reasoning tags or longer outputs, the immediate, maybe slightly cynical hypothesis pops up. Is the model just getting better scores because it's generating longer, more verbose rationales? Is it just hitting some kind of internal token quota rather than genuinely improving the quality of its logic? Did the study address this potential confound?
Yes, they address this directly and quite convincingly. The reasoning length investigation, which is visualized in Figure 4 of the paper, specifically tackles this just more tokens hypothesis. They plotted the distribution of the total reasoning lengths measured in the number of words generated for 2 groups of solutions on the AME24 benchmark, those generated by the original base Quen 2.57b instruct model and those generated by the model after being fine-tuned with SRL.
And what did the comparison show? Did the SRL model produce significantly longer outputs?
The key finding, according to the paper, is that the distributions of reasoning lengths for the base model and the SRL fine-tuned model show no significant difference. The curves representing the word count distributions overlap almost entirely.
Really? So SRL didn't make the model more verbose overall?
Apparently not. At least not in a statistically significant way on this metric. This finding is actually quite crucial. It provides strong evidence refuting the idea that the observed performance enhancements are merely an artifact of the model allocating a larger token budget, or simply being induced to produce more verbose, potentially rambling outputs at inference time.
So the improvement isn't just superficial length.
It strongly suggests the improvement is genuinely rooted in something deeper. The enhanced fidelity, the improved logical structure, and the higher quality of the individual logical steps that the model learned to produce via the dense, stepwise reward mechanism of SRL. The conclusion drawn is that the model learned to reason better, not just longer.
Okay, that's compelling evidence from the math domain, addressing length concerns and showing emergent behaviors. But a truly strong methodological finding needs to demonstrate generalizability, right? SRL was designed, in principle, to be domain agnostic, just needing that decomposition into logical actions. So the next critical test is, does it work in a vastly different, highly practical, and arguably even more complex domain, like agentic software engineering? The task here is fundamentally different. It's about training software agents to resolve real-world programming issues found in code repositories. They're typically evaluated on challenging benchmarks, like SW Bench. These tasks require not just code generation, but deep interaction with large code bases, potentially multi-turn interactions with tools like bash terminals, reading files, writing files, running tests. It's complex. Why is this particular domain known to be especially difficult for traditional RL approaches?
Yeah, the challenges in applying RL directly to agentic software engineering are numerous, and they're both technical and logistical. The paper touches on why direct online RL is so hard here. First, the context windows required are often exceptionally long. The agent might need to consider information scattered across multiple large files in a codebase just to understand the bug. Second, the environment feedback latency is typically very high. When the agent attempts a patch, say by modifying a file and running a command, verifying if that patch actually fixed the bug without breaking anything else requires running potentially slow build processes and integration tests. This slow feedback loop makes RL exploration incredibly time-consuming.
It takes ages to know if an action was good or bad.
Exactly. Third, the state and action spaces are simply massive and often quite unstructured. The state includes the entire codebase plus tool outputs. The action space involves deciding which file to read or edit, which specific lines within that file to change, what code to write, what bash command to run next. It's huge. These factors combined, long context, slow feedback, massive spaces, have severely constrained the development of stable, scalable, truly end-to-end RL systems for software agents. It's just very difficult to get a useful learning signal through traditional outcome-based RL.
So SRL, by imposing structure through decomposition and providing dense rewards, might offer a way around these obstacles.
That's the hypothesis. SRL attempts to inject structure in a more informative learning signal where the raw environment interaction offers very little, very slowly.
Okay, let's look at the specific SRL setup for SWE, software engineering, described in the paper. How did they define the logical action decomposition for this domain, and what training data do they use?
Right, so for the base model, they wisely chose Qwen 2.5 Coder 7b Instruct, a variant already specialized for coding tasks, giving it inherent proficiency in the domain. The expert data was crucial. They generated 5,000 high-quality expert agent trajectories. These weren't human-written. They were generated by a very powerful proprietary model, Claude 3.7 Sonnet, attempting to solve real issues from this SW Bench dataset. Importantly, these generated trajectories were verified to ensure they actually resolved the issues correctly.
So high-quality, machine-generated expert demonstrations. How are these decomposed into actions for SRL?
This is the key adaptation. Following the core SRL paradigm, they define the logical action as the specific environment-consumable command the agent outputs at each turn. This could be, for example, a command structured like function bashels defs function, or maybe function write file path to file.piece function, followed by the code content, or perhaps a specific command for an editor agent.
So the action is the concrete thing the environment can execute.
Exactly. And what about the natural language reasoning? The expert agent likely generated explanations or plans before outputting the command, right?
Yes, and that preceding natural language explanation, the planning, the rationale generated by the expert agent before it emitted the command that was created as the inner monologue that texts think apart, conceptually equivalent to the think block in the math domain.
Ah, okay, so the structure is natural language reasoning thing, followed by a structured executable command action.
Precisely. This decomposition was applied to the 5,000 expert trajectories. And because each trajectory involves multiple turns or steps, this process yielded a very large data set. They report 134,000 stepwise training instances suitable for SRL. That's a critical step. By defining the logical action as that specific structured environment function call, SRL fundamentally constrains the action space the policy needs to predict at any given step. It makes the optimization task much cleaner and more focused than trying to predict free-form natural language that might contain a command.
Absolutely. It simplifies the learning problem significantly. The observable state for the model at step dollar becomes the output from the previous command execution, and this state is directly relevant to predicting the next highly constrained logical action, the next command. The model gets a history, generates its internal thought process, the natural language reasoning, and then has to commit to outputting just that single correctly formatted environment action. The dense sequence similarity reward then focuses on ensuring the format and the content of that action, the specific bash arguments, the correct file path, the code block being written is as close as possible to the expert's action for that step.
Okay, the setup seems well adapted. Let's look at the evaluation and results for this SWE task, detailed in Table 4 of the paper. How did they measure performance and what did they find?
Performance was measured by the resolve rate, simply the percentage of software issues the agent successfully fixed within a given budget. They evaluated this in 2 different configurations to test different aspects of the agent's ability. The first was an Oracle file editing setting. Here, the task is simplified. The agent is told exactly which file contained the bug and need modification. This setup isolates the model's core capability to generate the correct code patch, removing the burden of finding the bug location first.
Testing the repair skill directly.
Yes. The second configuration was a full end-to-end evaluation. This used an agent scaffold they call Agentless Mini. Here, the agent has to do the whole job. Analyze the issue, identify the relevant files, file localization, and generate the correct code repair. This is obviously a much higher bar, closer to a real-world scenario.
Makes sense. And who did they compare SRL against?
Critically, they compared the SRL-trained Quen 2.5 Coder 7b instruct against a strong baseline called SWE Gym 7b. This baseline uses the identical Quen coder base model, but is trained using standard supervised fine-tuning, SFT, on the same expert trajectories, treated as monolithic sequences. This provides a very direct comparison between SRL and SFT on this agentic task using the same underlying model and data.
Perfect comparison. What were the results?
The results were, frankly, overwhelming evidence for SRL's effectiveness in this domain, too.
Bro.
In the simplified Oracle file editing setting, the SRL-trained agent achieved a resolve rate of 14.8%. The SFT baseline, SWE Gym 7b, only managed 8.4%.
Wow, that's almost double. 14.8 versus 8.4. Please.
It's not just almost double. It represents a staggering 74% relative improvement for SRL over the strong SFT baseline on the core patch generation task. This is a massive difference, and it strongly suggests that for agents needing to perform structured, multi-turn interactions, SFT's inherent rigidity in mimicking long sequences is again detrimental, whereas SRL's stepwise, action-focused mechanism successfully distills the complex chain of reasoning required for effective agentic behavior.
Okay, so it's much better at generating the fix when told where the problem is? Did that advantage translate robustly to the much harder end-to-end setting where the agent also have to find the file itself?
Yes, it did. The performance gain carried over significantly. In the full end-to-end evaluation, the SRL agent achieved an 8.6% resolve rate. The SFT baseline lagged significantly behind at only 4.3%.
So SRL doubled the end-to-end performance as well.
Exactly. Doubled it. This is critical validation. It shows SRL doesn't just improve the quality of the final code patch in isolation. It enhances the overall learned decision-making process of the agent, allowing it to better localize the problem within the codebase and generate the sequence of actions, file reads, edits, commands that lead to a verified fix. The generalizability of the SRL framework across abstract mathematical reasoning and concrete interactive software engineering seems convincingly demonstrated by these results.
That's impressive generalization. But we should probably pause for a moment to consider the necessary conditions, the prerequisites for SRL effectiveness. You hinted earlier that SRL isn't necessarily a magic bullet. It has constraints. What does the paper suggest are the requirements for it to work well?
That's an important point for practical application. The paper does implicitly and explicitly suggest that SRL's effectiveness is contingent on a couple of key factors, primarily related to the student model's initial capabilities and the nature of the decomposed data. First, the student model must possess a baseline competence in instruction following and format adherence. Remember the structured output SRL requires, think block, followed by a specific action command format. The underlying language model needs to be capable enough at the start to generally follow these formatting instructions given in the system prompt.
Why is that so critical?
Because if the model consistently fails to produce output in the required structure, if it just generates rambling text or forgets the action tags or mixes thinking and action, then the reward mechanism breaks down. It will likely hit that strong Navistal 1 penalty repeatedly for format errors, preventing it from ever accessing the informative, continuous Norris and dollars, his similarity reward for the action content itself. The dense reward signal is never reached.
So the model has to be trainable enough to even participate in the SRL process correctly before it can benefit from the density of the reward. It needs to follow the meta instructions.
Exactly. If it can't even follow the rules of the game, it can't learn from the score. Second, related to the decomposition itself. Although SRL aims to reduce task complexity by breaking the problem into steps, the resulting stepwise data must still allow the policy model to achieve good rewards with certain probability. Meaning the individual steps after decomposition shouldn't be so difficult or abstract that the base model has absolutely zero chance of generating an action that has any similarity to the expert's action for that step. The model needs to be able to, at least sometimes, generate an action that is partially correct or contains some relevant components, even if it's logically flawed overall.
So the dense reward mechanism has something positive to latch onto.
Precisely. If the model's generated actions for a step are consistently complete gibberish relative to the expert action, yielding near zero similarity scores always, then even the dense reward signal becomes uninformative for that step. The policy still stars for useful directional information, just at a more granular level. SRL works best when it breaks down a globally impossible task into a sequence of locally manageable intermediate tasks, where manageable means the model can achieve non-zero similarity rewards often enough to learn. #tag outro.
So wrapping this up, what does this all really mean for the ongoing effort to scale down the powerful reasoning capabilities we see in giant frontier models, making them accessible in smaller open source packages? Our deep dive today strongly suggests that Supervised Reinforcement Learning, SRL, isn't just some minor incremental improvement. It appears to be a genuinely robust and, quite impressively, generalizable technique. It successfully navigates that tricky space between the pitfalls of SFT rigidity on one side and the challenge of RLVR reward sparsity on the other, particularly when dealing with these really difficult reasoning problems, the Dotterguard category.
It really seems to thread that needle.
The core mechanisms we unpacked, the deliberate action decomposition, the clever use of a dense sequence similarity reward that focuses strictly on the logical action content, using sophisticated matching like difflib, and critically, the adapted dynamic sampling strategy that ensures training occurs only when reward variance provides a clear signal these elements combine to create a powerful and effective learning curriculum. The results clearly show this framework enables smaller open source models down at the 7 billion parameter scale to actually master complex multi-step problems that seemed previously intractable using standard SFT or RLVR alone. And its role seems particularly potent when used as that essential preparatory stage in the sequential SRL right arrow RLVR training pipeline.
I agree. And perhaps the most intriguing finding, beyond the performance numbers, is the empirical observation that SRL training seems to fundamentally alter the behavioral patterns of these models. The emergence of sophisticated reasoning patterns that interleaved planning, the on-the-fly adjustments, the reflective verification that's fascinating, it suggests that by forcing the model's output into this structured format, these discrete logical actions interspersed with explicit inner monologues, we've inadvertently created a rich, implicitly labeled dataset, not just of final answers, but of the decision-making process itself.
A trace of the reasoning.
Exactly. And this raises a truly important, maybe provocative question for future research, something that goes a bit beyond the scope of this specific paper, perhaps. The question is, now that we have the structured output, where we can clearly identify the specific logical action the model proposed at each step, can we leverage that structure to define even more precise, maybe more theoretically grounded, policy optimization objectives?
Moving beyond just sequence similarity or final outcome.
Potentially, yes. If we know exactly what logical action was taken, if Geo added variable x to both sides of the equation or executed getDiff command, could we move beyond standard RL algorithms like GRPO, which still ultimately rely on statistical averaging of rewards and advantages? Could we instead develop objectives that enforce specific logical consistency rules between steps, or perhaps use formal verification techniques or domain-specific validators to assess the correctness of the derived logical actions themselves, providing an even richer, more targeted signal?
like a more rule-based or logically informed RL.
Precisely. This concept of leveraging the process structure for optimization points directly towards what might be the next generation of process-based, or perhaps even rule-based reinforcement learning. A paradigm where the quality of the learned policy is defined more rigorously by the logical soundness of the learned decision chain, rather than just statistically correlating actions with final outcomes or overall sequence similarity. That kind of transition, if successful, could be the key to truly unlocking robust, complex reasoning capabilities, even in significantly smaller, more efficient language models. It's definitely something to think about.